they are of high dimension, which means that classical computation can have some, like probably like need many computational resources to really like accurately solve that kind of problem. That is why we want to actually explore like whether quantum algorithms can be helpful. And I would like to start with two examples of possible non-unitary dynamics. So the first example is still the quantum dynamics, but we just like focus on the open quantum dynamics. It's like so the system that in the mind is that so I just want to like our quantum dynamics defined in an infinite space or in a very large space. And then if like the space is very large, then actually it is computationally intractable. It is very difficult. So for example, like we have some problems from like scattering, have some problem in photo dissociation and network transport, and also in some like large reaction systems, so like the entire Hilbert space or the entire physical space would be very large. And to deal with that, or to make that to be computationally efficient, so one way is so-called this complex absorbing potential method. So the complex absorbing potential method is that so we choose a finite size box, or we choose some like finite domain over my full system, which might be in the infinite space, and then like we just study the dynamics on that finite box. And if we do that, we can see that so we must have some correction on my Hamiltonian due to the path of my system, or the outset part for in my system. So, and in this complex absorbing potential method, so they're just like kind of like using so-called this absorbing potential to like reflect the influence of your path of your full system outside that box. So this equation is the specific equation that we are using in the complex absorbing potential method. So you can say that so we have something which is very similar to the Schrödinger equation. We have the first two terms. This part is the standard real space Hamiltonian. However, we also have something like this. It is the absorbing potential, and you can see that. So for the first part, it is a Hamiltonian, but for the second part, we have an additional measuring unit, which makes that so we have both permission part and anti-permission part, so the evolution operator will be non-unitary. Okay, this is like the first application. The second example is actually from the fluid dynamics, is the convection diffusion equation. So this is kind of like a partial differential equation which describes the dynamics with both convection and diffusion process. So like we look at this partial differential equation, so we have a Laplacian operator, which is the diffusion term. It is kind of like appear also in the heat equation. So you can just view this as something similar as the heat transfer, and it is the diffusion part. And we have this kind of gradient operator. It is the convection term. And of course, we probably have some like external force or some extra source in my evolution. And if you look at this equation, you can see that so we have both permission part, which is this Laplacian operator, and also we have a anti-permission part, which is this convection operator, because it kind of like preserves something. So the evolution operator again becomes general and non-unitary. So this is like another example. And I would like to like previously set up the model that I'm interested in. That is, so the problem that we will discuss today is mainly this general differential equation. So we just have we have a time-dependent matrix negative A of t, and for this A of t, I do not assume anything else. I just assume this to be a matrix. And so if we make this A of t to be quite general, then like the dynamics can be non-unitary. But even for the general matrix, I can always write it down as the decomposition in its permission part and anti-permission part. So basically, like here, L and H are two permission matrix. So I'm just making this decomposition. But I can remark that. So this is not an assumption. It is just like a way of decomposition, because for any arbitrary matrix A, you can really define your L to be the average between A dagger, and H to be something like a minus A dagger over 2i, and make this decomposition to be true. So this is just kind of like a representation. And so this is the equation that we are interested in today. And so since it is no longer actually like we don't really have any like some quantum state structure, so we still have to really define what do we mean by solving this equation quantumly. So I would like to follow the definition in a HHL algorithm style. That is, when I say like quantum algorithms for this ODE, actually I'm talking about preparing the quantum state. Encoding its solution is amplitude. That is, my goal is to prepare this quantum state, and the amplitude is the normalized solution of my differential equation. Of course, this kind of definition is a little bit controversial, and probably I will just come back to this at the end of the talk. Okay, now we have our problem, and here's the main result that we have. So the main result is that, so although like in the general differential equation, our evolution operator is non-unitary, however, it can closely relate to the unitary problems or the Hamiltonian simulation problems. So the relation is that any non-unitary evolution operator, it can be written as a linear combination of my Hamiltonian simulation problems. That is like, so basically like if you want to like really simulate some non-unitary evolution dynamics, then what we need to do is that we just need to solve multiple Hamiltonian simulation problems or multiple quantum simulation problems, and then we just linearly combine them together. So this is something that we found, and I just want to like discuss this in a more technical version. That is, so we have this theorem. That is, so we have this decomposition of my general matrix, and this is like the main result, this equation. So on the left-hand side is the evolution operator that we have. And this is some kind of like order operator. It might be a little bit technical, but you can just do this as the exact solution of my original differential equation. And on the right-hand side, what we have is that we have an integral or weighted integral of many unitaries u of k. So this is kind of like, you can just view this as a continuous version of the linear combinations, just like a continuous linear combination, the integral. So now those u are just some unitaries, and those u's are defined through some Schroeder equation. And here in the last line, we have the definition of the Schroeder equation. And we can see that, so this Schroeder equation is closely related to the original matrix. And actually, we only made a small modification. So for example, if we see the anti-formation part, so here we still have negative IH, and the original one we have IH, so actually we didn't do anything on the anti-formation part. But for the formation part, we want to make it to be anti-formation, to be a Hamiltonian or something like that, so we just add a imaginary time unit I times frequency term k, and that's it, and this is the definition for my unitary operators. And okay, this is the main result that I have, and I want to show you like why this result holds true in general, and but this actually is based on a very technical proof. So I just want to like try to explain this in a little bit intuitive way. So I just want to like explain some like special cases of that formula. So first I would like make a simplification that I want my matrix to be time independent. Basically, like we just want to compute the operator e to the negative at, and of course a can be decomposed into L plus IH. And the right-hand side is the formula that I have in my previous slide, and is the linear combination of here's many unitary operators. So I would just like to explain why this formula holds true. So let's see some special cases or some simple cases. So the first simplest case is that, so if we only have the H part, that is, we just get rid of this L, we only have the anti-formation part H. And in that case, our evolution operator goes back to the Schroeder equation, to the unitary evolution operator. So this is just like a Hamiltonian simulation problem, and our equation becomes something like this. We just get rid of L. So and this equation is quite trivial. So it has nothing to do with like the combination of multiple unitaries, because you can see that in the integral we only have a single unitary which is independent of k. But like this equation trivially holds true because we have a kernel function 1 over 1 plus k squared, and this kernel function turns out to be so-called the probability distribution function of the Cauchy distribution. So the integral over the entire space is just 1, which means that this equation is kind of trivial. A second special case is like a little bit non-trivial. That is, if we only have the formation part L, and we just get rid of the anti-formation part I times H. So in that case, the evolution operator that we care about is something like e to the negative IT, and it is kind of like the imaginary time evolution operator. And in that case, our combination formula becomes something like this. And if you're familiar with the Fourier transform, so this formula directly follows from the Fourier transform, because on the left-hand side, we are doing some function like the exponential function, and on the right-hand side, it is in the form of the Fourier transform. And the reason that we are using Fourier transform is because we can get an additional imaginary unit and make the expression inside the integral to be unitary. So this is like nothing but the Fourier transform formula. And also I'd like to mention that, so this special case formula for the imaginary time evolution has already been applied in many like variational algorithms for imaginary time evolution. So here I just list like several like references, but But our formula actually holds true for a more general setting, that is, we can simultaneously have both Hermitian part and anti-Hermitian part. And you can see that to combine these two cases, it is not that trivial, because your Hermitian part and your anti-Hermitian part, they do not commute with each other necessarily. So basically, like, you cannot just like directly multiply these two formulas. Instead, we have to like carefully like examine the interweaving terms, and also like to establish the rigorous proof for the most general formula. Okay, that is for the linear combination of Hamiltonian formula. And next, I will just be discussing some like how to really like implement our formula. So like to implement this, of course, like since here we have a continuous version of the linear combination, like to make this to be a numerical scale, we first need to do some discretization. So this way, I can just use some finite sum to approximate my integral, or by my favorite numerical quadratures, or the simplest, maybe the Riemann sum formula, or whatever we want. And after that, so our formula will become exactly the discrete linear combination of unitaries. And then to implement that, actually, so for all the remaining parts, they are quite flexible. Like, for example, we need to implement our unitary operators, so basically they are just some Hamiltonian simulation operators, and you can just use whatever we want, like for example, the simplest Taylor formula, or some like Postdoctoral method. So those you can be implemented by any Hamiltonian simulation algorithms. And after that, we need to do this linear combination step. So I think there are like two approaches to do that. So one is by we still use the quantum subroutine, which is called the linear combination of unitary technique. So this technique was first proposed by Charles and Wig for Hamiltonian simulation problem, and it was later applied to solve some kind of linear systems problem. And also, like for this linear combination step, we can also use it in a hybrid fashion, use some like randomized method. I guess like we'll give one more talk yesterday on many randomization methods for solving this kind of problem. I guess I will use one of their methods exactly. This is called the importance sampling. Okay, so let me discuss in details these two approaches. So the first is the quantum subroutine, the linear combination of unitaries. So this is like a one-page introduction on what the LCU is doing. I will always like start with the toy example. That is, so we just want to do some linear combination. So what if we just do like this simple linear combination? We just have two unitaries, U0 and U1. We just do the uniform like superposition or something like that. So the way of doing this is that, so we start with some input state U0, and we add an additional axial qubit, and we first apply the Hamilton gate to create some superposition in 0 and 1, and after that we will do the control version of my unitaries. That is, we just like if my axilla is 0, then I will apply U0 on my system register, and if axilla is 1, then I will just apply U1. So after this control unitary, what I get is some quantity like this. And the final step is to create the linear combination. So to create that, I just apply another Hamilton gate, and then I will just have something like U0 plus U1 if my first axilla qubit is 0. But of course, I have some orthogonal state. That is, if my first axilla is 1, then we'll have something like U0 minus U1, which is something that I don't want. So the final step would be, I will do some measurement, do some post-selection, that is, measure my axilla qubit. So if I get 0, then I succeed, and the remaining part will be the state that I want. But if I get 1, then I just start over and do this again. So this is like a very common step when we like try to perform some non-unitary transformation using quantum devices, because like the general strategy is that we just want to like embed our non-unitary transformation into a subspace of some unitary transformation, and after that we will do some kind of post-selection. So we will have some success probability factor or some like repeats, that there will be some overhead. Okay, so this is like for the toy example, and actually the general case is almost the same as this toy example. That is, for this general case, we want to compute this Cj, Uj. Then what we need is that we need two oracles. The first is the state preparation oracle, just call this prepare oracle, which basically encodes the square root of my coefficients in the amplitude. So this is like a state preparation oracle. And in my toy model, so the state preparation oracle is just H, because like in my toy model it is a uniform superposition, so like the Hamilton gate serves as the state preparation oracle. And the select oracle is the controlled version of my unitary, so which is in my toy model is just this part. And I can just apply the same strategy, and we can verify that. So the output, if I measure my axilla register, if the measurement is 0, then the output would be something that we want. So this is like the general strategy of of the linear combination of unitary pattern. Okay, so this is for quantum implementation. And of course, we can do this using like randomized methods. So I guess I can go over this like very quickly because like you already saw this like yesterday in one per talk. So it's basically like we have our exact solution to be the linear combination of unitaries. And for example, if you're interested in computing some kind of observable, then you can just like do your computation to find out that so it is the linear combination of many observables with some fixed unitaries. And what we can do is that we use the randomized method that we sample the quantum circuits that we want according to this weight or this kind of probability. And after we sample this kind of index, so for each sample, we just perform the corresponding quantum circuit to estimate this kind of observable. So for example, we can use some Hartree test or some other way to estimate our observable, and after that, we will just like compute the average of all the samples, and it will give us like a hybrid implementation of our method. So the advantage of this hybrid implementation is that it is more suitable for early fault tolerance or in the near-term regime, because like in the LCU approach, so actually like in this LCU, so we need some like controlled version. We need a controlled version of all of my unitaries, which can be like a little bit crazy, but like here in the hybrid version, so we don't really need that control that control logic. Okay, so the next thing that I want to discuss is the generalization of our formula. So far, I always like focus on the equation with only this term, with only this matrix multiplying this solution term. But actually, like as I mentioned in the convection diffusion example, so in many physics models, we also have some kind of source term. So for example, like in the heat equation, sometimes we can have some heat source, and then like those source is only like a time-dependent function. And if we add this term, actually like our algorithm still works for that case. So the idea, so-called the Duhamel principle, is basically like the idea is that we can view this source term as a kind of a perturbation of my original equations without this source term. So here on the right, I have like a figure that is, so for example, like the top curve is the full solution of my equation with this source term, and the curve at the bottom is the solution of my equation without the source. You can see that, so here, this is like the original solution. And what we can do is that, for example, if at this S1 time, we add some perturbation of B of t, then this perturbation will be evolved by my homogeneous term, or by my part of this matrix A, and then it will be evolved up to, for example, like right here. And then like at different times, we just add different perturbation, and it will always be evolved by my homogeneous evolution operator, by my original evolution operator, and at the end, so the final solution will just be the summation between my homogeneous equation and all the perturbation terms. And you can see that, so here in the perturbation terms, what we need to do is just the time evolution for the homogeneous case, which is just like can be dealt with the linear combination of Hamiltonian simulation problem. So I would like to say that, so this general case is just a linear combination of Hamiltonian simulation, just like add another layer of the linear combination. Okay, so the last thing that I want to discuss is the comparison between our algorithm and existing algorithms. I want to make two comparisons. So the first comparison is with the quantum singular value transformation. So you may hear about that. This is a very powerful technique for performing like matrix function transformation. So it's basically like this quantum singular value transformation is performing some transform on your singular value of the matrix. But it is indeed powerful for many other problems, but for the differential equation problems, it is not that powerful. So the reason is because in the differential equation problem, what we are doing is actually an eigenvalue transformation instead of a singular value transformation. So there's like a difference between these two kind of transformation, and the QSVT only works when the singular value transformation somehow coincides with the eigenvalue transformation, and that is the case when my matrix is perturbation or anti-perturbation. So this corresponds to the Hamiltonian simulation and invariant time evolution. Of course, like our matrix can be more general. It can have both terms, and it can even be like time dependent. And our linear combination of Hamiltonian simulation can be applied to a more general setting. Okay, so the next comparison is like a little bit technical. That is, we want to compare our algorithm with existing quantum ODE solvers. So like to make this comparison, I want to start with a comparison between Hamiltonian simulation algorithms and the general ODE algorithms beyond Hamiltonian simulation. So because I found this comparison very interesting because they are using a completely different strategy for designing the algorithm. For Hamiltonian simulation algorithms, so many of us are very familiar with that. So this will start with a short equation. We have some input state, and on a high level, we just sequentially apply a set of unitary operators, for example, like Hartree evolution operators or walk operators. And after that, we are done for a single run, which means that actually the important thing is that so in each run of my Hamiltonian simulation algorithm, I only have a single input state, so I don't really need to repeat this kind of input state in the Hamiltonian simulation. But the story is completely different if you look at the general differential equation. So the reason is that if you do the same strategy, then in the general ODE, so those operators are not unitary, which means that we have some success probability issue for each step. And then for the overall long-time evolution, so the success probability will decay very fast and will probably even exponentially decay, so we just lose any beta. But instead, so what people usually do is that, for example, they usually start with a linear differential equation, and they do some type of discretization for this derivative, and transfer this equation to be a linear equation. You can see that, so now this equation is just like a linear equation between my ut and my next step, ut plus h, where h is a small step that I'm using for my discretization. And after that, so we have a linear system. Then I would like to transfer this into a large linear system of equations. But the solution of these equations is not a single final solution. It is so-called a history state. That is, we would like to consider u0, uh, u2h, all the way to my final solution. And then those solutions at different times, they linearly depend on each other, and then we can just write down this large scale of linear systems. And then after that, we can apply our quantum linear system algorithms. So for example, our theory HHL algorithm or some more advanced ones. So this approach works very well, but it has an issue in the complexity. That is, this algorithm heavily relies on the HHL algorithm or the linear system algorithm, and the linear system algorithm will require multiple copies of the right-hand side, or the multiple copies of my quantum state. So the reason is that, so for solving the linear system problem, let's say AX equals B, actually we are still solving the non-unitary problems, and then we still need some post-selection or some measurement, and that will require us to run my algorithm for multiple times, which means that we really need multiple copies of the input states. And this would make most existing differential equation algorithms to have high computational cost in terms of the state preparation. However, in our linear combination of Hamiltonian simulation algorithms, so actually we heavily rely on how we perform the Hamiltonian simulation problem. So we don't have this input state issue. And here's a little bit technical comparison, but I would just to quickly go over that. So it's basically compared with the existing algorithm, so our new algorithm has a better scaling in terms of the state preparation, just because we closely related our algorithm with the Hamiltonian simulation problem. Okay, I would like to conclude that today I just talk about the linear conditional Hamiltonian simulation approach. So the key observation we have is that for any linear non-unitary dynamics, it can be represented as a linear combination of Hamiltonian simulation problems, which means that you can just it makes us to believe that it might be promising for quantum simulation to be useful even for the problem beyond Hamiltonian, just do multiple quantum simulation and combine them together. And then discuss how to implement the algorithm by quantum subroutine or in a hybrid randomized fashion, and also our algorithm can achieve a low state preparation cost. Okay, with that, I'd like to conclude that. Thank you for attention.
Thanks for a great talk, Don. Does anyone have any questions for Don? I think it's just Don.
So it's nice talking to you. I'm just curious, because in physics, usually people care about using line dynamics. So you can also always split the problem to a non-conditional Hamiltonian, and also job problem. Somehow you solve this non-conditional part. Do you think it's an easy generation? You can easily generalize it to a contained job problem?
Yes, it's possible. Yeah, it can be straightforward generalized to the input equation. Of course, for visual input equation, I guess you can do the purification, consider the channel, and it is not not higher than the original Hamiltonian summation problem, but like with the jump operator, I believe that our curves can also be applied to that case.
Thank you.
Thanks for the nice talk. If you go back to the previous slide, which was the table, so you said the number of uses of the initial state is optimal for Q.
Yeah.
And that just comes from the fact that Q is the ratio of the norms of the time state.
That's right.
What are the first thing, the number of times uses A? Is that optimal?
Exactly. The first thing is the drawback of our algorithm. So the first thing is the primary context in terms of the matrix that we have. So for now, we assume some kind of sparse input or some like block encoded input, and then it turns out that so our algorithm has worse scaling compared to the state-of-the-art algorithm. So and especially in this precision parameter. So the reason for this is that so in our linear combination formula, so we have a kernel function. We have a Cauchy distribution kernel. So it is a quadratically decaying function, and also like that integral is taking over the entire real axis, which means that we need to truncate our integral at some finite size and to like make it to be numerically indivisible. And it is exactly that truncation makes this convergence to be linear because my kernel function does not decay very fast. So, yeah, this is like the main drawback of our algorithm, and it is definitely like a very interesting open question to like simultaneously achieve the optimal state perturbation cost and the exponential convergence in terms of accuracy.
So actually, I have a quick question about that last point. When you're evaluating this integral by quadrature as an LCU, I would think that you could sort of efficiently evaluate it over exponentially many quadrature points because there's a cost of doing, say, okay. But that's not enough to give you log scaling.
Oh yeah, the exact reason is, let me go back to find the formula right there. So the exact reason is that when I define my unitary, so the spectral norm of my Hamiltonian depends on this frequency. This is like my unitaries for large scale is oscillating very fast. So it's like this is the reason.
I see. Thanks. Okay, well, let's thank Don one more time and welcome to the next speaker.